Again, repeat and recap. Change in internal energy. This is Q. Q is heat, loss, or gain. Work. Work is defined as negative P delta V. So we're plugging this into there. Well, let's review the sign values and let's talk about endothermic and exothermic. Because endothermic and exothermic are related to heat loss or gain. Okay? Now you have to keep straight the system and the surrounding. If you reverse that, everything's wrong. Just that simple. You do 10 different things, it's all wrong. Everything's reversed. You can't get worse than that. It's like your answer is 10,000 and you have 1 times 10 to the negative 4th. You can't get much worse than that. Okay? So keep things straight. Let's take a look here for endothermic process. In an endothermic process, Q is positive. Here's what that means: energy from the surroundings into the system. Just think of it this way to start. If we have ice and we are at room temperature, heat always travels from regions of high temperature to regions of low. And by the way, heat and temperature are not the same. They're related to each other, but they are not identical quantities, as you'll see today. Okay? But notice high temperature, much lower temperature here. Notice the direction of heat flow. It's going from high temp to low temp, so there's heat. And notice that we get energy going from the surrounding to the system. Why do we call this positive? Because our frame of reference is the system. The ice is the system. If the system gains energy, in this case it's in the form of heat, notice we have a positive value. All right, so again, endo and exo are with reference to the system. If it was related to the surroundings, it would be the opposite sign. But we want to do what the rest of the world and Europe and the whole scientific community does. So here's our reference system right here. Surroundings everywhere else. I'm taking a lot of time on this because I don't want to fight misunderstandings for the next 3 weeks. In terms of, well, how'd you get that signed out? Okay. Well, obviously, this is gaining energy. That's why that's positive. Easy enough? Well, what about this? Let's take a look at a chemical reaction where we have CH4 plus O2, gas, gas. So they're the reactants. This is methane gas plus oxygen. This looks like a combustion reaction. Combustion reactions are famous for releasing large amounts of heat. Now, I said releasing large amounts of heat, and if we're releasing energy or heat from the system into the surroundings, notice the system is losing energy, so we have negative sign values here. Get the idea? If you have a stick of dynamite, that's the system. You light it, it explodes. The energy is going from the system, which is the dynamite, to the outside world, which is everywhere within I don't know, 50 square yards. But you got to keep in mind, you got to understand the direction of energy flow and relate it to the sign. Well, so here are the reactants. And we're going to do a little energy diagram here. So we'll put E here for energy, and we'll put time down here. Now, just on a qualitative level, if you pump in some methane gas and let a little air in, which has oxygen, and you spark it, it's going to explode, release heat and light, and the heat's going to travel from your little container to the outside world. In other words, the system is losing energy, the surroundings are gaining energy, and you'll get warmer. And don't get too close to that stuff. If it's releasing a lot of energy, it could be dangerous. Anyway, here's the reaction that would show a negative exothermic process for a chemical reaction. So here we're at high energy here. There's my E value. I hope you agree that methane has potential energy, right? This is a natural gas. I use it to cook. I used it to cook this morning. Oxygen is a fairly high energy molecule. Of course, when we talk about high and low energy, it's generally related to something else. So oxygen has much more energy compared to carbon dioxide. And these two reactants have much more energy compared to carbon dioxide and water. So generally, when we compare energy, it's not that meaningful to say a lot until you compare it to something else. Because you're comparing energy of that to nitroglycerin. Sorry, that's no comparison. Nitroglycerin has a lot more energy. Anyway, why doesn't the methane and the oxygen, why don't they, I turn on gas, let's say that the sparking mechanism is not working. You got the little click, click, click sort of things that's creating a spark. Say that's not working. This gas is entering the room and it mixes with oxygen. Why doesn't it just explode? Why doesn't it just react? The reason is, in order for these two to react, we got to go over this energy barrier. Once we get over this bump, then we can react and create low energy products. CO2 gas plus H2O liquid, we'll say. And here are products. Notice the products are lower energy compared to the reactants. Energy is neither created nor destroyed. If this has a lot of energy and this has less, energy has to be released from the system because law of conservation of energy. What do we call, and I guess we can go ahead and balance this too. Let's put a 2 out here, and let's put a 2. Let's put a 2 right here. Let's balance it. Again, the difference between the energy where you start and where you end, that amount of energy has to be released from the system, in our little test tube, whatever, into the surroundings. So let's put plus heat. Now, from first year chemistry, maybe, or maybe not sure, but definitely from first year biology, what's the name of this bump, the energy bump that prevents the gas from just hitting oxygen and poof? That, in other words, that kind of keeps this stable until we spark it, right? We've got the sparking mechanism, or we could just use a flame, right? And that would give us a little boost of energy, and then it's downhill from that process. It'll go, go, go until one of these runs out. Who remembers? Oh, how soon we forget. Yes.
Isn't it like activation?
Yeah, so we're going to write EA, and that's energy of activation. And again, the spark is what gets us to this point. And then once it starts, we back away and watch the heat, feel the heat be released, watch the light, and we're filling up with carbon dioxide in the room and water vapor. So it's a downhill process from that point. Now, this energy of activation could be this. Woo, way up here. Now, that's one stable set of reactants. You really got to add a bunch of energy if you want to see products. Or what about here, just barely above? That means these are going to be pretty darn unstable, and maybe just dropping it gets it to react. Now, what about this? What if there's a gigantic difference between reactants and products? Gigantic, go way down here. Huge amounts of heat are being released then. And more heat's released, don't the gases expand rapidly? Lots of heat with, what do you know? There's a gas right there. And if it's hot enough, that's not going to be a liquid, that's going to be a gas. And what if those gases expand, 50 square acres within a fraction of a second? That's an explosion. And sometimes that gas expanding knocks down walls. Or let's use dynamite to blow through mountains so that we can build a tunnel. It's just amazing. Well, what about this? Let's say we had to go up here and then the products are way up here. Wouldn't that mean an endothermic process where we have to push energy into the system to go get the products? This is exothermic, where energy is going to be released into the surroundings. What do we call this change in energy from here to here? That is our enthalpy change. That's delta H. Notice, don't include the activation energy. Well, you guys, if you do a change is always final minus initial. There might be one exception in this class all year where we do initial minus final, but that's not now. It's not for a while. So whenever you see a delta, it's final minus initial. So if you have this value, from this value, subtract the final energy minus the initial. Let's see, what if we have a catalyst? A catalyst does this. This is the EA with catalyst.